Okay, so I am starting the stream now. So welcome if you're watching. This is the Internet of Streams project where I work on a home wireless sensor node in embedded Rust. So on our last stream, I tried to work on getting DMA-driven logging going using some framing libraries that we had worked on previous streams, and ran into a couple problems because RTFM, the board support crate that I'm using, and the approach that I wanted to take for doing DMA-driven logging didn't all play nice together. And I spent probably the better part of an hour, maybe close to two, trying to get it working, and ran into some blocks, and I know what needs to be fixed, but I probably need to kind of get back and think about my approach. Let me move this away from my face a little bit. Think about my approach a little bit and probably talk to some people about how to approach this effectively. So the answer is going to be, for now, I'm going to cut and run. So the plan is to implement a less optimal but working logger, so I'm not stuck on logger for like 4 streams in a row, and then take some time outside of the stream to figure out what my plan of attack is and then fix it on the stream. But for right now, it didn't go as smoothly as I hoped. So in general, so what we tried to do before, what we were trying to do is implementing a serial logger. So implementing the ability to send log messages over the serial port coming out of the NRF52 that we have. That gets routed down to the debugger on our chip, and that debugger gets exposed as a USB serial port thanks to the debugger. So I would be able to either get text logging messages like I wanted, or I would be able to send binary data thanks to the framing and framing library COBS that we're planning on using. That PR actually did get merged, so in the upstream version of COBS, it is merged. I don't think they've done a release, so I probably am going to stick with my vendor code for right now, and then probably ping them and ask them to do a crates.io release soon. But what I tried to do before was a totally DMA-driven serial stream, basically. And this is really nice because it means that my CPU doesn't need to interact. So basically I can just shove bytes in a buffer as a CPU and then go off and do other stuff, and DMA and interrupts will just so this uses DMA and interrupts, and the DMA engine will just go ahead and automatically start sending those bytes out over the serial port, which is really nice, and it's low effort, which means that my CPU can go off and do other things like receive messages and things like that. The nice thing about this is it doesn't typically cause a lot of problems for timing, or I'm not wasting a lot of CPU usage just waiting around. And this is really ideal, but it requires a lot of moving parts to kind of understand how each other work, and none of them to go wrong, which was difficult to do in the hour or two that I had going there. So like I said, we're going to come back to that. I eventually want to get to this point, but I think I need to do some more strategy thinking before I do that on the stream, so that I'm not sitting here and staring at my stream and thinking while all of you are watching that. So the plan is to think about that. So there's really, for doing the logging, there's kind of 3 approaches, and these are kind of hardest to easiest and most performant to least performant. So the totally DMA-driven serial stream is kind of the ideal. The other idea would be using interrupts to manage serial output. So what this would be is we have the idea would be to basically have a small buffer that the DMA can use, because everything on the NRF52 is DMA driven. Essentially all the peripherals require you to use DMA in some way or another. The question is whether you have like fully automatic DMA or like one chunk of data at a time DMA. And I was going for you could send many times the size of the DMA line and it would work. The other option would be to use interrupts and to kind of maintain a queue, like not a queue that the DMA uses, but have like a normal FIFO queue that an interrupt could use, and the interrupt would be smart enough to kind of refeed and restart a transaction and then go off and so every time the DMA says, hey, I'm done sending that block of data that you're sending, the interrupt can come in and go, oh cool, I'll copy the next block of data and here you go. And that's nice because the whole CPU doesn't have to be waiting. It's still not 100% efficient because in the interrupt I need to copy out of one buffer and into another buffer. And it also means that I need to have like a 128 byte or 256 buffer in RAM, 256 byte buffer in RAM that's just dedicated to the DMA, which is a little wasteful. And like I said, I spent some time copying, but in the grand scheme of things, not an offensively long amount of time waiting. So that's kind of the middle option. And then the easiest option is just block. So every time we send a logging message, we just sit around and wait. And the reason that I kind of didn't want to do this to start at, so our processor's running at 64 megahertz, so 64 million cycles per second, and on ARM, most simple instructions take about 1 cycle to execute. They're kind of a 1 cycle per instruction kind of chip. So that's what our CPU is running at. The max speed of our UART is 1 megabit. So that 1 million bits per second, not counting some overhead. So the way we're using our serial is 8N1, which means for every 8 bits of data we send, so every byte of data we send those 8 bits of data, so 1 byte. We also send 1 stop bit and 1 unused parity bit, which means we send 10 bits for every 8 bits of data we send. So we have a 20% overhead on our serial port already. What this means is that it takes, so if we have 1 megahertz, that means there's 1 microsecond per bit. And so to send each byte, we need 10 microseconds per byte. And the thing is, because the Cortex-M processor is a 32-bit processor, and 32 bits is 4 bytes, which means, and we can do 1 copy of 32 bits per cycle, because a move on ARM is generally 1 instruction, and it's 1 cycle. That means we can send 32 bits per 1/64th of a microsecond. So that means that if we are spending 10 microseconds, we are spending 640 cycles for each byte we send out, which means if we send, the max size you can send here is 255 bytes per transaction. So if we were to send 255 bytes, and that takes 640 instruction cycles to send each byte, that means every 255 bytes that we send, we're wasting 163,000 CPU cycles that we could be off doing something else. And that's a huge waste, because we could be processing a whole ton of packets, or we could be doing a lot of math and stuff like that. But turns out engineering time is more valuable than CPU time. And at the end of the day, 64 megahertz, so actually 163, 200, so it's 163,000 cycles to send each 255 bytes, divided by 64 million cycles per second, means we are wasting a little over 2.5 milliseconds for each 255 byte message. Now, most of our messages aren't going to be that large. I'd say we're going to be pretty conservative with our logging, so we're probably going to be sending something like 64. So, I mean, 40960. So we're probably going to be burning less than a millisecond, but a millisecond is a long time to a microcontroller, but I'm also spending a long time explaining this. So the answer is, today, as quickly as possible, I'm probably going to put together a logger that just sends data blocking, and that is unfortunate, but you know, what are you gonna do? So that'll be good enough for now, and that'll give me some time to not spend 3 episodes working on a serial logger, and instead start getting to the fun stuff like sending packets over a wireless radio, or even blinking. So we still have this blinky lights from, I don't even remember which stream. So yeah, you can see our little blinky light there. So that's still running. I would like our board to be doing more than blinking lights, even if it's blinking lights and sending data. So the plan here is to make a little serial logger as quickly as possible and move on so I can start doing the fun stuff. And then eventually, someday, when I'm more inspired for how to set up DMA, or maybe I've had some other conversations with some people on how they think we should approach this, I can then come back to it and make this more optimal. So this isn't a blocker for us today. So to think of it from if I was doing this for a job, this is not a blocker today. So I probably should not be spending a lot of time getting this perfect now. I should be spending a little bit of time getting it good enough for now. And then I know that this is going to cause problems to me later if I am trying to do some really high performance stuff, like if I am trying to receive messages at the maximum rate possible. I can't be receiving messages if I'm busy sending data over the serial. So that's going to be problems for me later. Yeah, so these are all sort of problems, but not problems for today, so we're not going to tackle them today. So let's go ahead and get started. So I have, in my repo, I have made a branch called, check out UART. So UART is a branch that I have where I'm starting and working on that DMA stuff, but for now we've gone back to master. Status, let's see what I've put in here. I've got my vendored code. I guess I never pushed my, this is stuff I was just hacking on to see how it worked. I don't actually, I think, need to vendor. I don't think I need to vendor. Well, I guess for now I don't need to vendor it because it's not there. So these are submodules in the UART branch because I did need to modify NR52 how, but I don't. Also, I got a really nice email from someone who watched the stream who said, I didn't explain how I set up my environment. And you are totally right. I did not show how I set up my environment because, well, I didn't. But the big things, if you're looking to get started with this, I would go to docs.rustembedded.org. So here is the embedded working group, which I'm a part of, has put together a lot of resources for how to get started in embedded Rust. And in particular, this page, docs.rust-embedded.org, is kind of capturing all of them except for the really new ones, but we're still working on getting those set up. But in the discovery book and the embedded book, and I'll look at the embedded book now, we have a section for installation, so how to get started. So you can definitely follow these instructions. The board that we are using is this one in particular, the 7EM with the hard float. Excuse me. So the NRF52 is this one. So you will need to install Rust the way that they explain. So use rustup-rs. You'll need to install your embedded target. So this rustup target add thumb v7em. And then you'll need to go into OS specific instructions. Although I think, so you will need armnunny ABI. So we don't use the compile, and different Linux distributions, and I think even on Windows it's slightly different. We, for this project, don't need GCC, or even the GCC linker, LD. We are using totally a Rust and LLVM toolchain for everything except for the debugger. We are still using armnunny GDB because the LLVM debugger, LLVMDB or LLDB, can debug embedded code, but it doesn't have the capability of flashing code, and it would be really obnoxious to use a separate tool to flash code and then start debugging. So for now, we still use armnunny GDB. So you'll need to get that installed. On this board, you could use OpenOCD the way they explain it here, or this board actually comes with, there's a company called Seger that makes a product called J-Link, and the debugger on here is capable of acting as a J-Link debugger. So this STM32 down here can be a J-Link debugger. So you can go to the J-Link website and install their tooling. If you're on Arch Linux, there's a package in the AUR. It's like J-Link Software and Documentation is the name of the package. I'll try to update the README soon, probably with an install page, that explains how you get your environment set up, at least for Linux. I don't use Windows or Mac regularly. The embedded working group does maintain guides for those, but personally I use Linux for all of my stuff, so, or at least as much as I can. So I probably will put at least instructions on how to get set up on Linux on there, and then if anyone wants to submit a PR for, hey, I got it set up in Mac or Windows, I'll totally happily take a PR to add that to the or to the repository. So there's the JLink. Yeah, there's some UDev rules that you'll need, but the AUR package does that for you. Otherwise, you'll probably need to follow some instructions from Seger on how to get the UDev rules there going on Linux, or if you're on Windows or Mac, maybe you'll need to install a driver or something like that. I'm not entirely sure. I think on Mac, I just installed JLink and it worked, because I used to have a Mac. So that worked fairly well. And yeah, so you'll need JLink to talk to the debugger. You'll need arm-naniabi GDB to talk to your embedded system. You'll need to install Rust, and you'll need to install the target. I've also noticed that the utility SCC cache doesn't play super nice with embedded code. So for now, I would recommend you disable SCC cache if you're using that while you're programming with Rust. If you don't know what that is, then don't worry about it. Cool. So let's go ahead and get started, and let's see where we are and how much I need to start over. So we've got our sensor node, and we've got our main RS. So we have, what do we have now? We have a timer, and we have an LED. So let's first get a serial port working, just so we can see what a serial port looks like. So I pulled up so I built the docs. So again, if you are looking for, what's really nice in Rust is all of the documentation for most of these libraries is kept within the libraries themselves as doc comments and things like that, which means you can just type cargo doc open, and it will go ahead and build the documentation for every single one of your crates and the dependencies for them, and it will pop out with a web page like this. So your web browser will pop up, and it will have all of the crates that are dependencies of your project. And if this was a library, we'd probably have better documentation here, but for an application, there's not much. There's just kind of some auto-generated structures that are created by RTFM, which is not super useful. But what it will have is it will have the documentation for the hardware abstraction layer in there. So I'm going to go look at the UART crate, and let's go look at UART, because I want to go ahead and make a UART. So over here, I will need to, let's go ahead and start pulling in. So we know this is in UART. So I need to pull in UART, and I think I'll need pins as well. And then I know we export parity and baud rate as parity as UART parity, and I'm doing this because later I'm going to end up using the SPI port as well, so I know we are doing the same thing there, where it's called parity and baud rate as UART baud rate. So I'm just doing this to save myself some hassle later. And then I also know we're going to need to pull in the actual UART 0 peripheral. So as a reminder, the stuff that comes out of this HAL is the human is the hardware abstraction layer, but this is the human interface. So this is the kind of interface we would expect to use as a human. I want to send 20 bytes over a serial port. Whereas the stuff that comes out of the pack, the peripheral access crate, this is the raw hardware peripheral on our microcontroller. So this is like, not I'm sending bytes over a serial port, but I'm putting this byte at this memory address because that's how I control my registers. We need to include both, because the way that this works in Rust is Rust has a concept of ownership. So you are given, when you get these peripherals, or the devices RTFM calls it, so we get our device, which is the NRF52832 pack, you get all of these low-level peripherals because that's what it knows how to give you. But we have Rust's ownership model here. So to create a abstraction layer, we need to kind of trade our low-level interface for a high-level interface. And this says, to our high-level interface, hey, I promise it doesn't say I promise. The compiler is enforcing that we'll never use that low-level interface again, which means you can make certain abstractions and certain assumptions that no one's going to come in and change things. So you don't have to worry about always checking what state you're in, because if you didn't make the modification as the hardware abstraction layer, it didn't happen. Modulo any things like registers that change when the hardware changes. But in general, we make this trade-off to be safe in Rust. So you don't have like one hardware abstraction layer thinking that something is immutable and can never change, and then someone just changes it. So we exchange ownership of a low-level interface for a high-level interface. So I need both, because this high-level interface is generic, because we could have multiple low-level interfaces with the same high-level interface. Like if I had UART 1, 2, 3, 4, 5, whatever. This board, I believe, only has one, so it doesn't really make sense that we made it generic, but I think the NRF 840 might have multiple serial ports. I'm not sure. If not, it was just habit, because there are other things like the SPI ports, which are generic because there are multiple instances of it. So I need to, like with my other items, I'm going to go ahead and make this an RTFM resource. So I'm just going to call this UART. And this is, nope, autocomplete, that's not what I wanted. I'm going to make this UART, and I know this is going to be of generic type UART0. And I'm going to initialize this at runtime, so I'm not going to give it an initial value here. And to send this, again, I'm going to have to go look at we're going to be copying and pasting some code. So I had a good conversation, well, really Jorge, who wrote RTFM, or is the main contributor to RTFM, and Hanno Brown of Braun Robotics, who wrote the DWM 1001 BSP crate. We all got together at one of the embedded working group meetings, and we kind of raised this as an issue, and there were some discussions, and there's some possible ways forward for how to fix this, but it's not fixed today. So we are going to go look at this crate, and we are going to go look at the DWM 1000. And the nice thing about these docs is, even though I don't have the docs or the code checked out, you can hit source and we can get the source. So let's go look at UART0 and figure out where, because we're just going to steal its initialization code. So to create a new UART, we need to call the constrain method. We need to call the constrain, which is an extension trait, which basically takes ownership of UART0 and turns it into a UART, the high-level abstraction. We need to specify what pins, because on the NRF52, it's really nice. You can remap, I think, just about any functionality to any pin. So like on one day, these 4 pins could be a UART, and tomorrow they could be a SPI port. And it requires no rewiring of the hardware, which is really nice if you're rapidly developing things, because sometimes electrical engineers make mistakes. The rule of thumb that I've heard is it takes 3 attempts to get a circuit board right. Like that's kind of what you should. Sometimes it takes more, sometimes it takes less, but kind of as an electrical engineer, you're kind of guessing that you're going to need to make 1 or 2 or 3 hardware attempts at this. So a lot of times it comes down to software people to fix mistakes in hardware, just because it's so much faster to fix problems in software than it is in hardware. It could be one day or a week of code changes, where if we had to change the hardware, it might be 10 minutes to fix the hardware problem, but then we have to wait 2 weeks for the new circuit boards to come in and to be checked and make sure that they were assembled correctly. So this is really convenient. Just as general as a developer, especially working as on developer boards, it's also very convenient. So we've got our pins already, which is nice. And these pins are the ones that are mapped out on the actual board. So we know this is going to have to be this, and we know it does work. So we're going to say let UART0. Can I copy this without copying the line numbers? Because if I can do, oh yes I can. So let's just copy this because it's like 90% of what we need. Let's copy, paste. So we're going to take this, and luckily you can tell we have consistent naming schemes. So I've got my pins, I've got a UART. This is not going to be P because P is what we use in the board support crate, but in RTFM we use device. So we take device, we constrain. I am probably going to need to pull in the extension trait. Oh no, right, we have the prelude. So the prelude here preludes in Rust are kind of the, hey, these are all of the things you're probably going to want. Usually it's a lot of trait definitions and things like that. One of the trait definitions are these extension traits. And what I mean by extension traits are something where they're kind of like, so when you have a struct, it has methods with it, and it has normal functionality on it, like whatever the developer defined. Normally, when you have ownership, you can implement, so Rust has coherency rules, which means when you implement a trait, and a trait is kind of like an interface for a structure, when you implement a trait for a struct, you either need to be the one that defined the structure, so that makes sense because you said, okay, this other trait is some functionality, I'm going to figure out how to implement it for this structure, or you need to be the one that defined the trait so that you can say, hey, I know what the behavior is, I can look at that structure and I can implement the functionality that I need. And Rust does this for a couple reasons, but typically it's referred to as consistency, because you don't want someone else's code who's defined the trait in a different way to get confused when you've implemented things in two different ways, and it could cause problems because you've implemented the same trait on the same struct totally in different ways, because one library implements it one way and one library implements it the other way. The concept of extension traits is when you have the trait, so like in the struct that we're talking about, this timer 0 or UART 0 is defined in the pack. So this comes from the pack. But in the how, we want to kind of extend the functionality of that data structure, which in our case is an actual piece of hardware. We want to extend the functionality of it to give it this high-level interface. In this case, we use constrain, which typically consumes the low-level interface and produces a high-level interface. So these extension traits are creating it. Constrain is the convention we use in embedded Rust for extension traits to create a high-level interface. So long story short, we already have the traits, these extension traits, so we'll see something like timer xed or UART xed if we jump into the how and we look at UART, we'll see, yep, there's a trait called UART xed. And if I go look at the source, you can see very uninterestingly it consumes a self, and a self can be anything that derefs to this is some trait magic to make it generic. But essentially, we've implemented the extension trait for UART 0. So if you give us a self where the self is UART 0, then you'll get back a UART like high-level interface. Long story short, we have the ability to make a high-level interface. UART. So let's go ahead and make that high-level interface. So we can pick the parity, so we're going to choose 8 and 1. Last week I also talked about some problems. So at maximum baud rates, technically this goes up to baud 1M, which would be 1 megabit. But I can even already tell you that it's going to drop some bytes, which is not a problem for now, and that's nice because we get that minimum time that we talked about before. So actually in Python, that math that I was doing where I said 255 times 640. So Yateki is saying, I'm missing it again unless you stream for 2+ hours. I will not be streaming for 2+ hours. I got to leave in about 45 minutes because I have a late night call with someone around the globe. So Yateki, I won't be, only about 45 minutes more. But yeah, no worries. I'll probably stream sometime this weekend. I don't think I'm going to stream tomorrow. I'm actually getting a tattoo on my arm, so I will probably be gone at the tattoo for very many hours, and then I will be very quietly sitting in pain for the rest of the evening, so probably I won't be streaming tomorrow. Maybe if I'm feeling inspired I will, but I'll probably stream Saturday or Sunday. But yeah, let's see how far I make it. I've got about 45 minutes left. You can't see my clock because my face is covering it, but that's okay. So what I was saying is this math that I was doing where I said it would take 2 milliseconds is at the max speed of 1 megabit. The problem is if we want it to be more reliable, we're probably going to have to drop that down to like 115/200 or double that or quadruple that. I think I've gotten pretty good reliability out of... Actually, no. It drops less at this amount, but you still drop some. And at half this, so like I think like 230-400. It doesn't drop very often. So I'll probably live with that. That should be fine for now. Later, once I get some tooling going, what I may end up doing is be a little smarter, where the hardware actually keeps the last couple messages it sent, and it sends at the maximum rate. And if it drops like if it corrupts one packet out of every like 10 or 20, that's fine because we're running 8 times faster normally. And if we have to resend some old packets, we can do that. There's just some different trade-offs. Like if we wait for ACKs, like acknowledgements that come back, that means we have a lot of latency and we're waiting for the computer, which is Linux, which might take a couple milliseconds to turn around a message because it's not a real-time system. So we spend a lot of time just sitting doing nothing. Or if we send a bunch of data and it says, oh, no, the third back message that you sent wasn't good. That means I need to have a buffer length of at least 3 messages so I can always go back 3 messages. So there's, like in all of embedded systems, there's a lot of trade-offs here. But today, we don't care because we're not doing anything high performance. I just want to see hello world come out of my serial port. So we're going to use 115-200 from now. And we're not even going to use framing for right now. So I've got my baud 115-200. And cool, let's see how this goes. UART. I didn't actually, so UART equals UART. I don't know, I don't think anyone's asked before, but I'm using a tab completion tool. I don't remember what it's actually called. There's tab 9. So it's called tab 9. It's actually a paid tool, but the developer is really cool and wrote tab 9 in Rust, and has made it so that you can essentially use the pro version of tab 9 whenever you're working with Rust. So that's their way of giving back to the Rust community. So let's go actually tab 9. So tab 9 is all language autocompleter. It's actually a really cool tool, and I don't know what it costs. What does it cost? Free. $49 for a personal license, $99 for a business license. I like paying for the software that I use. So I mean, like I'm using Sublime Text here. I've used Sublime Text for probably close to probably 2010 or 2011, so like 8 years. So I bought Sublime Text 2 and then I paid for the upgrade with Sublime Text 3. There's another tool that I use called Beyond Compare, which does file diffing. I don't remember how much that costs, but I worked at a couple companies, had them buy it for me every time I worked at a company because it's so useful. And then at some point I just bought my own license. So even I'll probably go out and buy tab 9 just because I'm not going to do it on the stream because I don't know what credit card information I need to put in. But this is actually a really cool tool, and I'm pretty pumped about it. It's not smart in the way that RLS or Rust Analyzer is, where it actually understands Rust and it semantically recommends things. I think it uses heuristics based on just like, in your whole project, including all of your dependencies, I've noticed that like when you type dot after this variable name or this type or something like that, you usually pick this, which is really nice because it's less complex, because it doesn't have to understand Rust in the same way that a compiler understands it. But it gets things right more often than not. And the more often you repeat stuff and have more boilerplate, the smarter it gets at fixing that. So I'm not paid by tab 9, and I don't actually know who the developer of tab 9 is. But someone posted this on one of the Rust forums, and probably Reddit, and I saw it, and it was pretty awesome. And the fact that they let you use the pro version for free with Rust is pretty awesome. So I'm appreciative. So thank you for doing that for Rust people. It's probably convinced me to buy it. And yeah, if you have software tools that you use every day, like I use Sublime Text like 8 or 10 hours a day, yeah, pay for your tools. We're all software devs. That was my rant. Okay, so what I was getting at here, when I said 1 megabit, I'm gonna spend 2 milliseconds if I'm at 1 megabit. If I'm at 115-200, which is like an eighth or a tenth of that, then I'm gonna spend 10 milliseconds, which is a long time in embedded systems. So we'll see how that goes. Burp, burp, burp. Let's go ahead and cargo build. Let's see if I have UART. Did I not? UART 0. Oh, it's just UART. That's weird that it let me just put my 0 in the wrong place. Watch. Okay. Constrain UART pins. Did I already pull pins in? Okay. Sorry, got distracted by Twitter there. Where is my actual code? Pins. UART pins. This is the danger of copy and pasting code. Cool, so that works. So now we have this. So let's say every time we loop, what does the interface for this look like? I think I wrote this and I don't even know what it is. Read, write, send a TX buffer. Cool, so we need to send a TX buffer. Let's see, what is the easiest way to do this? Because this takes a U8 and we're gonna wanna write a string. Also, on the NRF52, does this version doesn't have the fix for this yet. Okay, on the NRF52, like I said, it has to be DMA for everything. But the DMA engine only lets you DMA out of RAM, not out of flash. So what this means, if I were to write something like let message equals like hello world with a new line, and I did something like UART dot what is it, send, no, write message dot as bytes dot unwrap. I could do this and it would totally compile. UART, not right, resources. It would compile if I typed the right code. UART. Right, I need to add it to the resources. I'm really trying to make a point here and I'm really screwing it up by not being able to write code. So this would totally work. The problem with this is that because, well, okay, no, actually I think this actually would work. Maybe, I can't remember how. I could do this. Burp, burp, burp. I could do this, and this would totally compile. The problem is this is gonna like silently fail at runtime because the DMA engine can only talk about RAM, and when you have a constant string like this, then it is always, it's just gonna be like, oh cool, that never changes. I'm not gonna put that in RAM, I'm gonna put it in flash. But because it's in flash, when you hand this memory address or as the slice to UART, the DMA engine is going to be like, oh, that's a flash address. No. I don't even think it throws an error, or maybe there's an error, but we're not checking it correctly in the library. In other versions of the drivers, and I think in newer versions, this is still the release 070 version. I think in the newer master branch, we've started moving over where at the top of each of these like write and read calls, we've made sure that the memory address that you pass in is in RAM. I also need to read the datasheet. If you are an expert at the NRF52 and you know if there's some like status register bit that gets set if the DMA failed to send something because it was on there, or if there's something on the DMA engine and you know that, let me know, because right now the kind of annoying thing is that we have to manually check it, so it's a runtime check. We actually look at the pointer address and we look at like the range of memory addresses, which is not a lot of overhead. It's a couple cycles, but you know, zero cost and all that. So I would rather have something that does the DMA transaction, and if there's some kind of status bit, then it returns an error. That would be really nice. So if you know if that's possible, let me know, or open up an issue on the NRF52 HAL repo, because we want that. But for now, what I'm going to do is, to get around this, I'm going to do a copy into RAM by making a slice which is going to be like 0 U8, and let's give it, we have a lot of RAM, give 512. So we've got this kind of like scratch, you got this scratch buffer. So we're going to do a scratch dot dot let message equals this. We're going to do this equals message dot len. So we're going to take the length of this dot copy from slice message. So what this does, if you're from a C world, this is essentially memcopy. We're saying like, hey, copy from slice expects both the slice that you are copying to and the slice you are copying from have the same size. So we make that happen by taking a slice of it, and then we copy the whole message into there. And then we're gonna have this new let ref message equals scratch. It's gonna be immutable to scratch dot dot message dot len. So now we can just we've got this immutable reference here that we can do, and then we're going to do this as ref messages byte. So now we know this is in RAM. A slice expected time, oh right, it already is a U8 slice because we don't have to convert from a stir, and then it's going to be as bytes. Because when you convert from a string slice to U8 slice, you need to use as bytes. So we have this now. So let's, you know what I haven't done? I haven't JLink, JDB server, burp, burp, burp. So we have our connected device. So we now have a connected device. We're building, let's do a, you know what we're going to do? We're going to CD Ferris, Internet of Streams, CD sensor node. We're gonna do a cargo run over here. Okay, so we're loading code here, and I'm gonna sneaky behind the scenes do a cargo build release. And I've noticed whenever I start doing compiling, the video of my stream starts getting a little stuttery. I think the audio quality holds up, but I probably should be using a much more powerful. I'm using like I use a ThinkPad X1 Carbon 6th generation, so it's like a quad core processor, so it's a pretty beefy dev machine, but apparently not beefy enough to do video encoding, streaming, and compiling embedded code at the same time. So I probably should go out and buy like a PC for streaming or something like that, but later. And if anyone actually complains, I guess let me know if it's unwatchable, but for right now, whatever. Okay, so I have that, and the other thing that I need to do is I need to actually look at my serial port. So I can do ls dev tty. So I've got ACM0. So this is mapped to my, I know that this is my serial device that comes off here. So there are better terminals, but let's split my screen here. And if I do, there's the screen utility in Linux, dev tty ACM0, and I give it a baud rate. Hey look, we have hello world. Look, we've sent messages. It's beautiful. It's not exactly a logger because I'm sending raw bytes and this is super inconvenient to use. But I am in fact sending bytes over a serial port and we don't see any messages going missing. So that's nice. Over here in cargo build release, you can't see it, but my CPU load right now is 14. So that's not great. So let's exit out of here. If I go to htop, you can see my my poor computer. My poor computer is not happy. Okay, cool. Well, that's what computers are for. So we notice that this is no longer moving. So I don't need this to be quite that big. So that's great. So git add -i. This, I don't think we have, no, we don't have anything worth adding. Git commit, basic UART, proof of concept. So cool, we have logging messages. That's not super useful. So what do we need to do? You know what we should do? We should break out of having one file. We should have some encapsulation. So let's touch source logger.rs. So let's make a nice little logger module, and let's start off by having like a pub struct logger. I'm sure I could get really fancy with macros and stuff like this, but with RTFM you have access to lots of your resources in a convenient number of places. So I'm gonna try and avoid using some macro magic, mostly because I'm not great at macros. I'm competent but not wonderful. But let's figure out. I need to pull in my UART definition, so I'm going to need UART and UART0, because what I want my logger to own. So it's just going to have a field called UART, which is going to have a UART0, which means I need to pull in. Actually, let's just see. All right, in main, I need to do so in Rust to say, hey, I've added this other file. Do mod logger. Now when I save, Rust check should give me an error. I was hoping. I'm also using Rust autocomplete, but it's probably slowly dying because of my. Okay, let's use nrf 52 hal UART use, where is that? Let's just, I don't mind copying and pasting from my own code. Burp, burp, burp. Cool, that works. Pub struct logger. Yeah. Impl logger. Pub fun new. It's gonna take a UART. You know it. Yeah. UART 0. It's going to return a self because this is just, you know, a very vanilla logger. Self UART. So I used a couple things. You can use self in a bunch of places when it's simple. And if the names match already, you don't need to say like UART, or UART, because this is silly. Just do this. There's probably a way even. There's probably like. This changes all the time, but there's probably an easier way to do this, but whatever. Okay, so let's, for now, let's have some methods like log pub fun warn and pub fun error. Sure. These should, I suppose, return some kind of result. Result. Burp, burp, burp. I don't know. I'm gonna have some kind of. I'm gonna have some kind of result. Probably some kind of something. But and then I'm gonna have a not pub function called fun send, which may just end up being right, but you know, let's give ourselves a little bit of indirection. This is going to take an and self, and it's going to take buff, which is a slice of U8s, and yeah, it's going to turn a result. This is probably overkill because probably maybe in this stream I'll do something different for these different ones. So let's have an and self and buff that you want to send. Let's actually be, let's be nice, and let's take an answer here, because that'll be easier to use at a level. So for now, let's just do self.send data.as bytes, and this is going to have the same result, and this is going to be self.uart.write buff. Let's see if that complains about different error types. It's going to be, yeah, this returns a UART error, so we're going to use .map error. So this says if an error occurs, then essentially you're going to call this closure. We don't care what the result is, and we just return this, which says, like, no matter what error you get back. So if you have not an error, just an OK, return what was there, which we know is already OK because both of these take, they both take an empty tuple. But if you get an error, substitute that error for this, which is an empty tuple type. I think there's also a name, kind of like Turbofish, for this. It's like the slug or the house or something like that. If you know what it is, tell me in chats. But yeah, cool. Yeah, these are all never used. Tell you what, let's for all of these. Nope. Let's just for fun, let's do a self.send. I'm gonna have to do this make sure it's in RAM thing again. So this is also gonna have a, let's call this scratch, and this isn't great, but let's have a, I know we need 255 bytes, so let's this is gonna be a U8 of 255. I guess let's just handle this in the copying down here. So we're just going to send log space log or the born space. Let's make this even. This is going to be error space, and then self.send. This is not the most efficient approach to programming, but hey, that's not our job today. Our job is a proof of concept for a home hobby system. So let's keep it reasonable here. So let's actually I could just make a static. Don't really want a static, because if I was making multiple of these, then it'd be a problem. But I know I'm not, but whatever. Let's just burn some stack space. It's not like we're restricted in any way. Okay, so UART, for our initializer, you need U8, 255. Can I do this? I saw someone do some funky things with expected slice. What do I have to do? Burp, burp, burp. I guess I have to do that. Dot as bytes. Right. That's gonna be wrong. Yup. Right. I'm gonna have to do that for. Okay, enough. I know I'm wrong. Okay, so there's two things. I don't need to put this one here. I don't need to put this one here. I'm sure I would, if I was sure there's a more dynamic way to, okay, more typing, less thinking, or more thinking, less talking. So this is going to return that, and then this is going to return that self scratch, right? Scratch identifier. Huh. Okay, I saw someone doing something weird things where they put an underscore where I didn't expect it to be. Oh, 0 U8. Here, maybe? No. Okay, whatever. I know what it is, but do we expose? Is that exposed anywhere in sensor node? Do we expose that in 5.2 HAL, target constants, easy DMA size? Awesome. So instead of magic numbers, let's do that. So because we have different targets, so if you wanted to port this to like the, I don't know, the 840 or the 810 or something like that, target constants, easy DMA size. So instead of using 255, and I know I'm going to also need use core comp min. Cool, so that's their right buff map error. So I need to do the copy to scratch thing. So what do I need to do? Let's see, for C in buff dot chunks easy DMA size. So this will give us an iterator of the items, and if it's less, then it'll give us less. Then we are going to that, and we are going to do, we know that it's never going to be bigger than that, so self dot scratch dot copy from slice, right? But we just need scratch from, yes, thank you, but it's buff.len, not scratch.len. Dot copy from slice. Well, no, it's just C actually. So just copy the slice into RAM. And instead do that. Yeah. Are you happy? No, you are very not happy. Expected a result. Why did you expect a result? Who's respecting it? Oh, right. So that's right, because we're doing this in a loop, which means now I need a one of these. Core comp min. Yeah, I guess I don't need core comp min anymore. I was going to use core comp min to like figure out what's smaller, the amount you're sending, or the amount of things, but actually using this chunks iterator is super nice. It may end up being not the most optimal thing, but hey, it works, and we're not optimizing today. And I also realized that this is one level deeper, so let's burp. We have a UART, we have a target constants, we have this. I need to like, let's go look at, I want to look at I think that might be a nicer fit to how do we do this in chunks? For 52832 HAL source, I know spim was, oh, not lib, that's not what I want. Oh right, it's going to be in common anyway. HAL common source spim spy master. Yeah, so you can see we use right. So we use this while offset. I wonder, I might make a note to use chunks, because this is just pleasant. It's a lot less like manual. I'm going to open up an issue. Issues. New issue. Consider using using chunks method for sending data. for things like spim transfer, this is a handy pattern I came up with. Not sure if it compiles to more code. For sending multiple blocks of data for things like this, Rust, this. Is the GitHub online editor nice enough to do this? No, it's not. So we're gonna do Shift Tab, copy, undo. Let's get rid of our leading white space. Yeah, something like that. Okay, well, I should probably have actually made sure that actually works. So let's go, and we know our easy DMA size is that. We need a long message. So I've done this test before, but have you ever heard the story of Darth Plagueis? Sure. Also, don't go and know your meme. I just know this is a fairly long block of text. Copy, go away. That's enough, know your meme. Let's make sure that this is okay. This is just some dumb meme from like prequel memes or something like that on Reddit. So let's make a const meme stir equals, yeah, thanks. Oh no, you are such a long line. Meme and stir. And stir. Right. So let's actually, okay, now we actually need to do a couple things. So we have our logger, we have the ability to send. So for main, we need to, instead of having a UART, let's just have a logger, which is going to be, we don't need a generic type on this. This is just going to be a logger. We have mod logger, use logger. So we've created our UART. Logger is going to equal logger new UART 0. Yep. And then for right now, let's just resources, don't take the UART, take the logger, because UART doesn't exist anymore. Logger dot, I don't know, log. Let's just do all three. Because we actually have to pass it a stir now and not a U8 slice. And I explicitly want to take it one out of flash so that should it be self dot, so someone in chat is maybe saving me from myself. Self dot scratch c dot len logger scratch buff dot len. Yes, you are very right. I should not have used buff there. Thank you, Meek, in chat. You saved me from being very confused here in a second when it probably would have crashed. Well, this first test of it would have worked because it's less. And also write, this should also be buff.len or c.len. Let's do this because I find this more readable. C, because we should do this. Shadowing, right. Okay, I think that's right. Thank you, Meek, for catching that. Main. Okay, so let's just do a basic test of our abilities here, and log warn error. Constant item is never used. Yeah, thanks. Cargo run. Let's do a release now because we're not debugging anything. So we've got our log warn error, so that's nice. Let's also slow this timer down. Let's slow this timer down to 500 on the on. Let's get rid of stale comments and 500 on the off. Or I guess the other way around, but so now we've got like a 1 hertz tick. That looks awfully like it's panicked. Big num. Wait, who's using big num? Sig trap. Well, no, that's my breakpoint. Okay, so let's look at our, where's our GDB? Debug GDB. Do not continue. Do not pass go. Yes. I am not debugging, so this is going to be interesting, because if this works totally fine in debug mode, something is likely getting optimized. Who is optimizing something from me? What is using big num? Cargo tree. Big num? Big num? Okay. So something is optimizing something. I bet you there is a... Well, that's just plain unfortunate. I wonder if it's trying to elide the reads there. Because it's like, oh, this is just a... Let's throw a hammer in here that I really hope does not work. Rust sync fence. I don't want atomic fence. I want compiler fence. Compiler fence. So compiler fence is something that you usually don't need. You usually only need it when you're writing something like DMA driven code. And what it does is it says like, hey compiler, I'm doing something weird here. Don't optimize across this bound. So if I do a use core sync atomic compiler fence, and I need to use a core sync atomic, is it in here? Ordering? Yes, ordering. So let's just, in the really obnoxious case, let's do a compiler fence ordering. Really, this is one of those things where I do this first, and I really hope this doesn't work, because this would mean that something really weird is up. Let's put that there. Oh, that makes me sad. Oh, that makes me sad. That means that the optimizer is doing something very wrong. If I remove these, libcore num big num. Okay, what happens now if I do this? Just to continue. Oh no, you're just totally fine. Did my serial port just get out of sync or something? I wonder if my serial port just got out of sync or something. That's worrying. Okay, well, we'll pretend that I didn't see that for right now, and we'll hope that that was just like my serial port got confused or my operating system got confused while I was under too high of CPU load. But okay, I am running cargo run release. Yes, cargo run release. Okay, well, sure. What else can I do? I've got about 5 or 10 minutes because I've got a call in about 15 minutes and I'm gonna have to stand up before my call. So we're gonna have to come close to wrapping up. Let's get our big message sending, and then if our big message sends, we'll call that a win. So we've got our meme. We know that log, warn, and error all work, so let's just get rid of these lines. We don't need 3 memes. Let's log meme. Yep, so this shows that we're able to send big messages. And let me quick show you what Control A quit. I'll show you what the kind of message loss that I'm talking about when you run faster, because you should see it pretty regularly here. So if I change this to 1 million, so now I've got my screen. Or release. Let's just run. So you can see like there's some junk characters there. There's like Dark Lord got some stuff. Like we lose a lot of bytes. Like let's halt this just so I can pick one of these. So like logger, let's go up into main, let's copy this line, let's get rid of this, copy this, move it up. So let's turn off word wrap. So we can see about how often, so play just the wise, I thought not. We lost 3 bytes there, a byte there, a byte there, a byte there. Yeah, so you can see, I mean, we're losing 1 out of every, I don't know, we get little runs every little bit. I don't know if that's like the UART is not, what I'm guessing is the NRF52 UART's fine. I'm guessing either the STM32 UART is not fast enough to reliably keep up with that, either at a hardware level or at, it just doesn't have enough memory buffer where it just like it gets over full, or USB just is not, whatever low speed USB that they're using does not have a high enough throughput to handle debugging. And you know, that's a good point. Let's see what happens when I'm not debugging, if it's any better. So we'll leave this here, because I'm about to wrap up anyway. So let's Control C. This is fine. We'll just close out of this. We've got this. So let's Control. No, I was thinking maybe if I didn't debug, whether it would be more reliable because there wasn't as much data going over USB, but it's still garbage. So, I could do this for lower bandwidths, but I don't know. It's going to be unreliable at some point. But overall, I'd say Control A, quit. Control A, quit. Overall, successful stream. I got some logging going. I've got a message. I don't have variable messages yet. Let's clean up these messages real quick. We don't need this scratch buffer. We don't need this. We don't need this. Let's just do a quick cargo check just to make sure. Oh, right. I need to clean up my... Hopefully I never need these again. Import UART in main.uart. Okay, yep, because we're not thinking about UART anymore in here. We also are not thinking about UART in here anymore. The types are just elided. Go check. Ordering logger. Did I not hit save? Save. Cargo check. Okay. Git add -i. No, let's revert the changes on debugger. That's fine. Git commit. Logger. Initial simple logger module. Okay, so this is a blocking logger module. It's not, it's not a dream, but it gets the job done, and we can send long messages or short messages. I didn't show it here, but we could use the core format macro, or not the format macro, but we can use the write macro. So if you have your own scratch buffer, we can use the format macro, which is nice. Excuse me, format macro, write macro. So we'll show that next time where we do some basic, and actually I probably clean this up and use write instead because this is overkill and not super efficient. But again, we're not worried about efficiency here. We're worried about getting the job done. And obviously this won't work for sending binary data because we have we're using that new line terminator that I said was a bad idea. So maybe we'll switch this over to maybe the next, well, no, I want to move on from logging. At some point when I get stuck somewhere else, we'll come back and we'll make this COBS. We'll write a little desktop client where instead of using screen, we'll have that, and we'll pump out JSON messages or something like that so they're easier to parse. I don't think we'll do that next stream unless I'm entirely uninspired, but I think next stream I want to start sending hello world over the radio. So I want to have two devices that can kind of just send data to each other. And then we'll save improving the logger as something that can be done later. But what we have now is good enough for now, I think. Unless I run into a problem where I need something better. But for right now, good 50 lines of code. Okay, thank you very much for watching. As a reminder, so I've never, I should have done this at the front. If you are still watching, in Berlin, in a little over a month and a half, there is going to be, my company, Ferris Systems, is running a conference called Oxidize Conference, which is an embedded Rust conference, the first embedded Rust conference as far as I know, here in Berlin, Germany. So oxidizeconf.com. So yeah, it's April 26th through 29th, 2019 in Berlin. Tickets are on sale. We have just finalized our selection of CFPs. We are going to be sending out the notices to that shortly. So in the next week, we hope to have the speakers finalized. So we'll have our list of speakers. We'll also have, if you're interested in learning about Rust, you can come check out the workshops. I'll be giving one of these. This is a full day workshop with hands-on using actually this exact board, and we'll be doing a lot of the things that we're doing in the stream right now, but with some of the other training material we have put it together. So if you're interested in embedded, if you have the time to come out at the end of April, it would be great to meet you in person. You can meet me and a lot of the other people in the embedded working group who are going to be there. So we would love to have you. You can buy your tickets here. Thanks for letting me plug that. But yeah, I've got to run. So thanks again for watching the stream, and see you next time.